Hi there. This video is on section 11.2, where I'm going to show you how to write and analyze a series. And we're going to start with what a series is, which is essentially the sum of a sequence. We looked at sequences in our previous video, 11.1, if you want to check that out. I'm also going to introduce the first two tests for convergence of a series. They're called the divergence test and the geometric test. We're going to learn 8 or 9, depending on how you count, different tests for whether a series converges or diverges. And first two are in 11.2, and we'll do another couple in 11.3, etc. Okay, so first let's talk about some definitions, just so we are talking the same language. A series, which they use writing this sort of Greek capital S, is called a sigma. Sigma an, as opposed to, remember, a sequence was with the curly brackets. A series is the big old S sigma symbol. And so sigma an is the sum of the sequence. So they usually start at 0, so A0 plus A1 plus A2 plus A3, etc. If you add all of those sequence numbers together, that's called a series. We have a similar definition for a series that converges. A series converges if it equals, which in this case is a sum, not a limit, if the sum of all the numbers is equal to a single finite value, and it diverges if it's anything else. If it doesn't converge, then it definitely diverges. That's the only two possibilities. So a sequence is a list of numbers, and we analyze a sequence by using a limit to look at sort of where the sequence is tending towards. A series is a sum of numbers. We're adding a bunch of numbers together, and we analyze a series by seeing if the sum is a finite value or something else. All right, let's talk about our first two tests for the convergence or divergence of a series, of the sum. Series is the sum. So the first one, a lot of students get confused, but it's actually one of the more important ones that we use quite often right here. If the sequence has a limit that's not equal to 0, then we know for sure that the series diverges. So if you have a sequence of numbers where the limit does not equal 0, anything but 0, then immediately we know that the series of those exact same numbers, if you're adding them together, it does not equal a finite value. Okay, so that's called the divergence test. A lot of times we start with that because it's very easy to find a limit. And if it's not equal to 0, you're kind of done. You know the answer is the series diverges, and there's no need to do further analysis. The second test is called the geometric test, and it's for a very specific type of sequence or series. So if the numbers in the series, right, the numbers you're adding together, have a pattern of C times R to the n, where C is any constant and R is a number that's between 1 and -1. Oh, there's a typo here. This should say 1 and -1. Lost my -1 there. All right, let me write this up here just so that I don't confuse more people. So this should be -1 R1. Apologies for that typo. Kind of an important thing to have there, correct? So once again, if you have a very specific sort of series of numbers, you're adding these together, where each of the things we're adding looks like C times R to the n, where C is any number and R is between -1 and 1. So it's a decimal or fraction, but it cannot be larger or equal to 1. It cannot be smaller than or equal to -1. So definitely some small fraction or decimal. Then we automatically know that this particular series will converge. So a series of C times R to the n always converges, so long as R is between -1 and +1. By the way, if it does converge, we know exactly what the limit is. The actual sum is this thing right here. Oops, let me zoom in first of all. And right there. So if r is between -1 and 1, then we immediately know that our series will converge, but we also know the actual sum of those numbers. So, I mean, we're looking at an infinite number of numbers we're adding together. If they have this pattern of c times r to the n, where r is between -1 and +1, the sum of all of those numbers is actually equal to c over 1 minus r. Pretty neat. Not so hard to actually show, by the way, that it's equal to c over 1 minus r. I can show you the proof. It's also in the book. If you're curious, you can let me know, and I can run you through it. But that is the sum of a geometric series of numbers. And the fact that it converges as long as r is between -1 and +1 is called geometric test. And by the way, a note for this geometric test, if r is not between -1 and 1, if r is greater than 1 or less than -1, if it's sort of the other possibilities for r, we immediately know that the series diverges. So if you have this particular type of number sequence that you're adding together that looks like c times r to the n, c is a number, r is a number. If r is between -1 and 1, it converges. If r is not between -1 and 1, it diverges. Very nice, very nice. Okay, and we have the bonus of we actually know what it converges to if it does converge. Let me first of all give you some examples of some series, some basic analysis, and then we'll go into some more homework type problems where we'll give you a random series and we'll analyze whether it converges or diverges. Okay, so I think I have maybe 5 or 6 examples here of series. You notice that they're all being added together. I think I need to zoom a little bit more. Okay, so the first series, the things that we're adding together are 3 over 10 to the n, and it says start at n equals 1 and keep going to n equals infinity. So you might notice that this is n equals 1. If I stick in 1, I get 3 over 10 to the 1, which is 3/10. N equals 2 would be 3 over 10 squared, or 3 over 100. N equals 3 would be 3 over 10 cubed, which is 1,000, et cetera, et cetera, et cetera. Now, I did this problem in the previous video as a sequence, and the sequence ended up tending towards 0 because the limit is what we use to analyze a sequence. I had 3 divided by a larger and larger and larger number. This is not a sequence. This is a series. And students who are first learning sequences and series in Calc 2, they oftentimes get these two jumbled up a little bit. So if I'm trying to overanalyze or over-explain the difference between sequences and series, that's just from my experience of students often struggling getting the two of them confused at points when they're studying it. So we are looking for adding these together. The first number, when n equals 1, 3/10, I'm going to write as a decimal just to sort of make a point. And we're adding it to the next decimal. 3 over 100 is 0.03. That's 300ths in decimal form. 3 over 1,000 in decimal form is 0.003. Tenths, hundredths, thousandths. You can start to see the pattern, etc. So if I add all these together, you may notice that when you're adding decimals, you just add the tenths place together and the hundredths place together. There's only one non-zero number in the tenths place. That's a 3. There's only one non-zero number in hundredths place. You might also think about the fact that just adding these together is going to give you 0.3333 forever. I'll put the little bar here to say that 3's go forever. That is the sum of this series of numbers. And 0.333333 going on forever, you may remember as equal to 1/3. All right, so this is a series of numbers that converges because it has a sum equal to a finite number. Okay, so there's our first example of the series. Second example right over here, 1/2. So we're doing 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2. Very simple pattern here. What is the series of 1/2, 1/2, 1/2, 1/2, 1/2, 1/2, adding them all together? What is that equal to? The answer is it's equal to infinity. If I keep adding a half, I know it's a fraction, but if I just add 2 of them, I get 1. If I the next two 1/2 plus 1/2, I get 1. I'm going to be adding 1, or I can group them together more ways and get big numbers bigger than 1. I can group 3 together and get 1.5. I'm going to be adding these numbers forever. 1/2 plus 1/2 plus 1/2, or 1 plus 1 plus 1, or any way you want to think about this. It's just going to get bigger. It gets 0.5 bigger every single time forever. And so that's going to equal to infinity. So this grows without bound, is what they say. There's no stopping. There's no top number. If you think 100 is the top number, it's going to get past 100, right? I'm going to add 200 halves. That's 100. And another half is 100.5. It goes beyond 100. Any number you give me, it grows beyond that bound. So this thing diverges. It has no finite value equal to the sum. Diverges. All right, the next number, or next series, is 1 over 2 to the n, which if you want to think about n equals 1, n equals 2, n equals 3, I know n equals 1, equals 2, n equals 3 because it says start with n equals 1 and plug it in. N equals 1 gives you 1/2. N equals 2 gives you 1/4. N equals 3 gives you 1/8. We always count by whole numbers there, starting with whatever they tell us and going to the end point, which is almost always infinity. So here's a bunch of fractions. The fractions before 1/2, 1/2, 1/2, 1/2, they diverged because they added well, without bound. What about these guys? 1/2, 1/4, 1/8. The numbers get smaller. Does that affect anything? We don't really have a lot of tools yet to analyze whether a series will converge or diverge, but I'll give you a geometric argument about why this either converges or diverges. It's going to turn out to be converging. So I'm going to make a square, and the square is going to be 1, the side length is going to be 1. So it's 1 by 1 by 1 by 1. That's my square. And now what I'm going to do is I'm going to take the midpoint here, and I'm going to connect all those things. And since those are the middle points, the midpoints, I'm going to get another square with exactly half of the bigger area. So this one here, this blue thing right here, is going to be 1/2. So this part over here that I'm going to shade in, I'll shade it in with green. Here, 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 here. Each of those is exactly 1/2 altogether. So that's 1/2. All the green stuff added together is 1/2 because I connected all the midpoints. So each of these segments is 1/2, and I get them all up, it's half of the whole thing. Okay. So, or you can just imagine this is like an individual square like this. It's half of that square. Each square it's a half of. So you can also do it that way. The green shaded section right here of all this sort of outside part is exactly equal to a half. And the inside part is still a square. So I'm going to repeat this process. I'm going to take the midpoints of each of these interior square lengths, and I'm going to connect them. And once again, I get a half of the resulting stuff. So I'll do this here in red. So this here, the outside portions, they're going to be half of this sort of inside square. They're going to be a half of a half. They are 1/2 of a half. Or in other words, they're 1/4. So I shaded in sort of this outside area in green. I got a half. The inside square here, I divided it again and got another half of that half, which is 1/4. And yes, I can continue doing this process by connecting these together and shading in, these outside areas. That's going to be half of the previous guy, which is going to be 1/2 of the 1/4, or 1/2, 1/2, 1/2, however you want to write it. So we have 1/2 plus 1/4 plus 1/8. And if I do the next one, if I have enough space, it's going to be 1/2 of the 1/8, which is 1/16. So this geometric shape I'm drawing is the same as 1/2 plus 1/4 plus 1/8 plus 1/16. And what is equal to 1/2? Well, that's the shaded area. The shaded area of this stuff right here is the 1/2. And if I add in the next thing, that's 1/2 plus 1/4. And if I add in the shaded part of the next part, that's 1/2 plus 1/4 plus 1/8, 1/2 plus 1/4 plus 1/16, 1/8 plus 1/16, etc. And so, however many times I do this, I guarantee you that the total area I'm shading is less than or equal to 1, because the entire square has an area of 1, and every time I'm shading part of the inside of this 1 by 1 square. So this is going to be less than or equal to 1, and we can actually show, so later, even today, we're going to show this is equal to 1. And because it's equal to a finite number, we know it converges. This is going to converge. The sum of all those numbers is equal to a finite value, which is actually equal to 1. I'm not going to use any fancy math to show you it's exactly equal to 1 right now. I'm just trying to give you an idea of what a series looks like and how to think about them in terms of converging and diverging. All right, so that's a geometric argument about why the sum of 1/2 plus 1/4 plus 1/8 plus 1/16 is in fact equal to 1. Let's do a few more examples, and then we'll do some actual homework looking like problems. All right, so next up, we have a series from n equals 1 to n equals infinity of 2 to the n. So sticking n equals 1, we get 2. Sticking n equals 2, we get 4. So 2 plus 4 plus 8 plus 16, etc. It's kind of like the previous one, but instead of fractions, we have just the whole number. So instead of 1 over 2, we have 2. Instead of 1 over 4, we have 4, etc. So 2 plus 4 plus 8 plus 16 plus 32, etc., etc., etc. So what happens to this thing? Well, it keeps getting bigger and bigger, right? I add 32, it gets bigger. I add 64, it gets bigger. Does it ever stop? Does it stop at 1? No. In fact, it gets bigger than 2 to begin with. Can it bigger than 100? Well, yeah, because I'm going to be adding 32 and then 64, and then I'm going to be adding 128, certainly getting it bigger than 100. This grows without bound. Or you could say that the sum tends to infinity. So this diverges. I'm not trying to do homework type problems. I'm not giving the justification that you would give on a homework, but I am trying to help you understand how we think about series. All right, 2 more examples, kind of important examples, in fact. So next one up here, I have n equals 1 to infinity of 1 over n plus 1, which is when I stick in 1, I get 1 over 1 plus 1, which is a half. And then when n equals 2, I get 1 over 2 plus 1, which is a third. So I get a half plus a third plus a fourth plus a fifth plus a sixth, etc. When we did sequences of numbers, the limit of the sequence was equal to 0. That's in the previous video in 11.1. But this time we're doing the sum of these numbers. So 1/2 plus, 1/3 plus, 1/4 plus, 1/5, etc. So how do we know whether that converges or diverges? Once again, I'm not going to be using a official like mathematical formula to do this. We're just going to talk about how to think of these series. So you might want to think about some of the previous series, first of all. The series where we had 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2, this guy right here, that diverged because it keeps growing bigger and bigger and bigger. We made the numbers get smaller. So instead of making the same denominator 2, 2, 2, 2, 2 each time, we get 2, 4, 8, 16, 32. That ended up converging. The sum was equal to 1. So this one has numbers getting smaller. So instead of 2, 4, 6, or 2, 4, 8, 16 on the bottom, we have 2, 3, 4, 5, 6 on the bottom. But the numbers on the bottom definitely get smaller and smaller and smaller. This limit is definitely equal to 0 if I was thinking of this as a sequence, but we're not doing a sequence, we're doing a series, which is adding things together. So how do I think about adding these things together? Well, this is a very famous and sophisticated series. And here is a very simple argument. Once again, this is not part of your homework. I'm just helping you understand the intuition behind a series. So this, give me a little chance, will help you understand what the heck the series are. because we're doing series for all of chapter 11, and it's nice to have an idea of what we're doing before we start jumping into all the weird formulas that we're going to be doing. All right, so this first number here is clearly a half, right? I don't think there's any doubt about that. For the second couple of numbers, I'm going to group these two together. We have 1/3 plus 1/4. And if you think about them, 1/3 plus 1/4 is 4/12 plus 3/12, which is 7/12, which is larger than a half. So 1/3 plus 1/4 is larger than half. I'm going to do it a slightly different way. Instead of 1/3 plus 1/4, I'm going to write this as 1/4 plus 1/4. I made the first denominator bigger. So 1/3 turned into 1/4. And remember what we talked about in the previous page, right? If you make the denominator bigger, right, then the resulting number is smaller. So 1/4 plus 1/4 is smaller than 1/3 plus 1/4. 1/4 plus 1/4 is exactly equal to 1/2. Let me just make a little bit more space down here. So this is 1/2, and 1/4 plus 1/4 is a half, but we no longer have equals because 1/4 plus 1/4 has a larger denominator, so the result is a smaller number. So our sequence, our series 1/n plus 1 is going to be smaller than this thing right here, right? So our sum of numbers, 1/2 plus 1/3 plus 1/4, etc., is going to be smaller than 1/2 plus 1/4 plus 1/4. All right, hold on 1 second. All right, I confused myself, and I got like, wait, I got to pause and think about this. Okay, because I said it backwards. In fact, I think I said it right, but I wrote it backwards. So let me just make sure that I don't confuse myself and anyone listening and watching this video. So once again, I've made the denominator smaller. So 1/3 plus 1/4 is larger than 1/4 plus 1/4, right? I made the denominator smaller, so the whole thing, I made the denominator larger, so the whole thing is smaller. So this thing is greater than or equal to this, right? So my original series, 1/2 plus 1/3 plus 1/4 is larger than 1/2 plus 1/4 plus 1/4 because I made 1/3 into 1/4, which is clearly a smaller number. So the original series is smaller than this one here. All right, sorry for that confusion. I did mess up myself and I had to pause to straighten myself out. We're gonna, instead of picking the next two numbers, we're gonna pick the next four numbers, and we're gonna write these all as 1/8, 1/8, 1/8, 1/8. So there's four numbers here. One of them is exactly equal to 1/8. All the other ones became smaller. 1/8 is smaller than 1/5. 1/8 is smaller than 1/6. So again, this is going to be a smaller sum. And 1/8 plus 1/8 plus 1/8 plus 1/8 is 4/8. But instead of writing 4/8, I'm just going to simplify that and write that as 1/2. So the next four numbers added together are going to be, you know, the original series is going to be larger than this 1/8 plus 1/8 plus 1/8 plus 1/8, which is 1/2. And I could do the same thing with the next eight numbers. The next eight numbers, I'm going to make 1/16 plus 1/16 plus 1/16. And those are going to all add up to 8/16, which is again 1/2. And I can continue this taking the next 16 numbers and making those all greater than all less than the original value. So we have a sum that's greater than 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2. Hopefully you follow that without too much distraction from my original backwards inequality sign. So we know from our original discussion up here that we know from our original discussion up here that 1/2 plus 1/2 plus 1/2 plus 1/2 forever grows without bound and therefore diverges. Our series here of 1/2 plus 1/3 plus 1/4 plus 1/5 is greater than 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2. So whatever our sum is has to be larger than 1/2 plus 1/2 plus 1/2 plus 1/2, etc. Forever, right? This could go on forever. But we know that 1/2 plus 1/2 plus 1/2 diverges. It equal to infinity. Diverges. It grows without bound. So our series is larger than something that diverges to infinity. Therefore, we know that this thing diverges. Diverges. So this series, 1/2 plus 1/3 plus 1/4 plus 1/5, is called the harmonic series. It has a name. You'll hear that very often. And there are many, many ways to show that the sum is not a finite value. In the next video in 11.3, I'll show you a couple new series convergence tests, one called the integral test, one called the p-series test, and we can show that this harmonic series of 1/2 plus 1/3 plus 1/4 plus 1/5, etc., diverges using either of those two tests. But I didn't want to give you sort of a non-fancy formula version, just by saying, hey, we can group these together and show that its original sum is bigger than 1/2 plus 1/2 plus 1/2 plus 1/2. 1/2 plus 1/2 plus 1/2 forever is equal to something that diverges. It's infinitely big. So we know that our series, which is the sum larger than infinity, is also got to be infinity. It's also got to diverge. Okay, so there's an argument about the harmonic series diverging. All right, one last bit of intuition here, or at least explanation. I'm trying to throw in a few things here. This, by the way, this idea that you have a series greater than a diverging series is called the comparison test. We're going to get that in 11.4. So I'm trying to also give you ideas about things that are coming up. So these aren't just random arguments. I'm trying to sort of foreshadow things that we'll be doing in future sections, just to let you in on the secret. All right, last one here, we have what's considered an alternating series. We have -1 to the n, which we have talked about several times before. -1 to the n, if n is an odd number, you get -1. If n is an even number, you get +1. So you get -1 plus +1 plus -1 plus +1, etc. So if we look at the partial sums, in other words, if we start summing, the first two numbers summed together is equal to 0. The first three numbers summed together, if I start adding from left to right, -1 plus 0 plus -1 is equal to -1. If I take the first four numbers and add them together, -1 plus +1 plus -1 plus +1 is equal to 0. And you might already start seeing the pattern. If I took the first five numbers and added them together, they would equal -1. So if I look at the sum, just like going along, just sort of adding them up, we call them partial sums. We're not adding the whole thing yet. We're just adding parts at a time to get an idea of what's going on. Adding the first two numbers, the result is 0. Adding the next number in, so adding the first three numbers gets -1. Adding the next number in, so we now have four numbers total, the sum is 0. Adding five numbers total is -1. Adding six numbers total would be 0. So our sum is going between 0 and -1 and 0 and -1. So the sum alternates between 0 and -1. So depending on how far I go, either I get a sum of 0 or -1. So if I add all them together, add all infinite -1 plus 1, -1 plus 1s together, I'm not sure what the answer is, but it's either going to be 0 or -1, because it's always one of the two, right? Either I get 0 or I get -1. I can't say it's an average of those two because it never is equal to a half or -1/2. It's always have a sum of 0 or always has a sum of -1. But if you remember our definition of converges, it has to equal a single finite value. It cannot be a combination or a multiple or different versions of a finite value. You can't have choices. It's got to have a single value or it does not converge. This alternates between two values. It's either 0 or -1. So therefore, it diverges. So this series diverges. The sum does not equal a single finite value. It alternates between two finite values, but that unfortunately is not converging. All right, so we do have things that alternate back and forth, and we're talking about alternating series and how to analyze them again further along chapter 7, chapter 11, whatever chapter we're in. All right, let's see some homework example problems to sort of get you more in line with what you'll be asked to do on the homework. All right, so I have a bunch of series here, and we're going to determine if the following series converge or diverge. And I'm going to be using these tests now. The divergence test, which just to remind you, if you have a sequence where the limit of the sequence does not equal 0, right? Just the limit does not equal 0, then the series automatically diverges. It's called the divergence test. And the other one is if we can write the series in a specific sort of pattern, c times r to the n, where r is between -1 and +1, we know that that series has to converge. And in fact, we know what the sum is. It's c over 1 minus r. And if it's not r between -1 and +1, it's anything else, we immediately know that that series diverges. That's the geometric test. Okay. Oops, next page. Might want to write those down or have those handy. I do have a list of the different convergence tests on Canvas as one of our resource pages you can download and have next to you, where it lists all the different convergence tests in one spot. So that way you could have them written down for you. But having in your own handwriting and the way you want to write it with the letters you want to write it and little notes next to it can also be very useful. All right, let's stop stalling and look at the first example, n squared over n plus 1. So if I stick in n equals 1, a lot of times I recommend students just write it a couple terms. N equals 1 would be 1 squared over 1 squared plus 1, which is 1 over 2. The next one would be n equals 2. 2 squared is 4. 2 squared plus 1 is 5. We'll do one more. 9 on the top, 10 on the bottom. So this is the numbers, or I shouldn't put commas there because we're adding together. We're adding all these together. We're adding 1/2 plus 4/5 plus 9/10 plus whatever the next one works out to be. So we're adding all those numbers together, seeing if they are going to equal a finite value. So those are fractions. The denominators are getting bigger, which is nice. So, it gives us some hope. It's not going to be like obviously equal to infinity or something like that. Let's see if we could test this. Well, as I mentioned before, one of the most common tests is the divergence test because it's very easy to do. The divergence test, to perform the divergence test, all you have to do is look at the limit as n goes to infinity of the sequence, not the series. So I just take the n squared over n squared plus 1, and I look at that sequence and see what the limit is. This is, well, if I stick an infinity, I get infinity in the top. Infinity plus 1 is infinity on the bottom. So I have an infinity over infinity situation, which, as you may remember, we can use L'Hopital's rule. I can differentiate the top. Let me write my limit. The derivative of n squared is 2n. The derivative of n squared plus 1 is 2n. Well, I know what 2n divided by 2n is. That's just equal to 1. So this is the limit as n goes to infinity of 1. And what is the limit as n goes to infinity of 1? Well, 1 has no n's in it. It does not care what n is. 1 is the constant. It's 1. So if n is 7, this is 1. If n is a million, this is 1. It's always 1. So the limit is equal to 1. All right. So the limit of the sequence n squared over n squared plus 1 is equal to 1. What does that tell us about the series n squared over n squared plus 1, which is 1/2 plus, adding all this together? Well, the divergence test, if you have it in front of you, or if you remembered it, or if you want to jump back to the previous page, if the sequence has a limit that's not equal to 0, we immediately know that the series diverges. So immediately we know that this thing, so this sort of adding up, this sequence of numbers must diverge. And if you like to know the logic, essentially what the limit is saying is that these numbers, 1/2, 4/5, 9/10, they're getting closer and closer and closer to one. So we're basically end up adding something very close to one, and then something close to one, adding one, at least something very close to one. You're adding things that are basically equal to one over and over and over again, and you're going to quickly grow without bound or diverge. So my first example here, the sum of n squared over n squared plus 1 is a diverging series. Okay, let's look at another one. Okay, let me just check this. All right, very good. The sum of n equals 2 to infinity is our next example. And once again, I'm going to write out just a few terms. This is certainly not what the author of your book does, and some students don't like this because they think it's a waste of time. I do think it's very informative. It gives you an idea of what's going on, and for some problems, it really helps you see what the actual path for solution is. So it may take a few seconds that are a good investment. So we start at n equals 2, by the way. We're not starting at n equals 1. You can see very well, if you have very good eyesight, or if you zoom in here, you can see that we're starting with n equals 2. So we're getting 1 over 2, 1 over n, where n starts at 2, and then n is 3, n is 4, n is 5, etc. So that's the sequence, excuse me, that's the series from n equals 2 to n equals infinity of 1 over n. All right, let's try the divergence test. I'll call it the div test because I'm lazy and don't want to write the whole word. We take the limit as n goes to infinity of the sequence 1 over n. Well, that's going to be just 1 over infinity, which is 0. So the limit of the sequence is equal to 0. So what does that tell us with the divergence test? Let's go back and look at the divergence test real quick. The divergence test says if the sequence is not equal to 0, then we know the series diverges. The sequence has a limit not equal to 0, then the series diverges. That's all it says. There's no part where it says if the sequence does equal to 0 that we know anything. All we know is if the sequence has a limit not equal to 0, we know the series has to diverge. So the divergence test, half the time or more maybe, will not tell us if the series diverges, because if the limit does equal to 0, we don't know anything. This doesn't only tell us something if the limit is not equal to 0. So in our particular problem, our limit is equal to 0. So the divergence test tells us nothing. I ran a room. Nothing. So I did this example because it's very common for students to think that just because the limit of the sequence is equal to 0, that tells us something about whether the series converges or diverges, but it really tells us nothing when the limit is equal to 0. In fact, you may remember this series 1/2 plus 1/3 plus 1/4 plus 1/5 in my previous example on the last page, where we did the harmonics, we call it the harmonic series, 1/2 plus 1/3 plus 1/4 plus 1/5. And I showed you just by grouping things together that the sum of this harmonic series was greater than infinity, and therefore the sum was equal to infinity, or in other words, the sum diverged. So this diverges. This is the harmonic series. It does diverge. So this, he's red. This diverges. And by the way, it is acceptable in the math community by saying it diverges because it is the harmonic series. What's the harmonic series? The harmonic series is 1/2 plus 1/3 plus 1/4 plus 1/5. It's very specific. It's not like any random pattern. It's specifically the numbers on the bottom go up by 1 every time. So 1/2, 1/3, 1/4, 1/5, 1/6. Very famous series, has its own name. It's called the harmonic series. If you see that, you could just say, hey, that's a harmonic series. I know it diverges. As I did promise you from the last page discussion, I will prove to you that the harmonic series diverges using both the integral test and the p-series test, but that will wait until the next video. Right now, I'm going to go on with the next example. All right, so the second example here diverges, and I showed it from the previous page, and you can also just say it's a harmonic series, therefore it diverges. Okay, we have 3/4 to the n. That's our next series, and we're starting at 0 and going to infinity. So sticking in 0, if you stick in 0, you get 3/4 to the 0. By the way, 4 to the 0, like any number that's not 0 raised to the 0 power, is equal to 1. So 4 to the 0 is 1, 5 to the 0 is 1. Any number raised to the 0 is equal to 1, with the exception of 0 raised to the 0. That is an indeterminate form. So if I stick in 0, I get 3/4 to the 0, or 3/1. So this is 3 as my first term. My second term would be 3/4 to the 1, which would be 3/4. The next one would be, I should put a plus in there. Next should be 3 on the top because it never changes. The bottom is 4 to the next number. So this was 4 to the 0, 4 to the 1, 4 to the 2. And then we're going to get 4 to the 3, etc. This is essentially like an exponential. It's 4 to a number, 4 to the 1, 4 to the 2, 4 to the 3. The base 4 is always the same, but the exponent gets bigger and bigger and bigger. That's like 2 to the x, or e to the x, or 4 to the x in this particular case, right? That's an exponential. I would prefer if they called this kind of thing exponential, but the name they give it is geometric. Now, geometric has a very specific format. I'll just write it up here just to remind you. Geometric looks like c times p to the n. That's what the geometric looks like. I'll put a little something here just so you can remember that it's a type of series, but it's c times p to the n, where c is a constant, p is a number. If the number is between -1 and 1, we know it converges, etc. So what's going on here? Well, we have 3. We'll write this as 3 times 1/4 to the n. Or in other words, we can write this as, I'll just do this, 3 times 1/4 to the n. So if you use algebra, you can simplify 3/4 to the n to 3 times 1/4 to the n. So the 3 is always a 3 is always a 3, but the over 4 to the n is really 1/4 to the n, which is the same thing as 1/4 to the n. And this is c times r to the n. Anytime you see a constant raised to a variable, 1/4 to the n, 3 to the x, it's got to be a number on the bottom, which is the base, and a variable as the exponent. That's exponential, right? 1/4 to the x, 1/4 to the n is an exponential. They don't call it exponential. They call it geometric. But geez, I wish they would call it exponential, because then I think students will remember it more often, because they know what exponential, it's like 2 to the x, or e to the x. It's a number raised to an x. 1/4 raised to the n is the same thing. It's an exponential, aka it's geometric. Okay, we're gonna call it geometric because that's what the book calls it. All the math people call it geometric, not just the author of our book. However, because it's geometric, we immediately know whether this converges or diverges. R is between -1 and 1. That's our R value right there, right? Remember, R is the number being raised to the exponent. It's the base. R is between -1 and 1. So we know immediately that this thing converges. Oh, my pen disappeared. I'll pause the video and see if I can get my pen to wake up again. 1 sec. All right, my pen hath awoken. So because R is between -1 and 1, we know that this series of 3 times 1/4 to the n converges. In other words, our original series, which looked like 3 over 4 to the n, since it was equivalent to 3 times 1/4 the n, we know this series converges. And that, my friends, is the geometric test. If it looks like this kind of exponential thing, a number times a number raised to the n, and that base number is between -1 and 1, we immediately know that this series, this sum, is a single finite value. All right, it converges. In fact, we know more. We actually know what that value is. Remember, in the previous sort of description I gave, I actually said that if it does converge, then we know that the sum is C over 1 minus R. So the sum is C over 1 minus R. It's not a lot of these tests tell us what the actual sum is. They just tell us whether the sum is a single finite value or not. So mostly you're just going to be saying, yeah, it converges. It's some value that I'm not really sure what it is, but I know it's a finite value. For this one, we actually know what it is. It's C equals, it's the sum is equal to C divided by 1 minus R. And ampersand, and you're going to move over for me? Maybe not. And we know the sum equals C over 1 minus R. In other words, the sum is equal to C. C was the number in front, which was 3. R is called the ratio. It's that base number. So 1 minus 1/4. So the sum is the constant value C divided by 1 minus the R value, which in this case was 1/4. So this is 3 divided by 1 minus 1/4 is 3/4. And 3 divided by 3/4 is 4. So the sum of all these numbers is equal to 4, exactly equal to 4. Right? So 3 plus 3/4 plus 3/16 plus 3 over 64, I think, plus 3 over 256, if my memory is correct. Those numbers all add up to, if you add all the infinite ones, they add up to 4. But nonetheless, it definitely converges, right? Even if we didn't know it adds up to 4. But we do. But even if we didn't, it would converge. All right, so there's an example of a geometric series, or we use the geometric test on this particular series to show that we knew it converged. So that was our third example on the lecture notes. All right, so the fourth example is basically the same as the third example. I didn't do this by accident. I did the same thing. There's a very, very subtle change. It starts with n equals 1 to infinity as opposed to n equals 0 to infinity. So I no longer have the 0 term in there. So I no longer have the 3. I have 3/4 because the first value I can plug in is n equals 1. So I get 3 over 4 to the 1 power. And then I get 3 over 4 to the second power, etc. So this is my sum. This is my series. It's the same as the previous one, except that it's missing that n equals 0 term. In other words, it's missing the 3, which was the result when I plugged in n equals 0. So this is also C times 1 over 4 to the n, right? This is also that formula where C is equal to 3 and the ratio or the radius is equal to 1/4, right? So it's still 3 times 1/4 to the n. Oops. This is C times R to the n. Has that format of C times a number to the n, where the C value is 3 and the R value is 1/4. So it must diverge. So we know this. Maybe it's getting too late for me to do videos, but so this thing converges. So by the geometric test, it has an R value that's between -1 and 1. We know the series converges. All right, so this series converges right here. This converges. All right, so why did I do the same problem twice? I did it not only to kind of remind you that it often doesn't really matter where you start, in terms of converging and diverging. If you're starting at 0 and it converges, then almost certainly if you start at 1, it also converges. And vice versa. If you start at 0 and it diverged, then starting at 1, it's going to diverge also. It doesn't really matter where you start from in 99.9999% of the times. The reason why I did this really was to talk about the sum. Remember, we talked about the sum being like C over 1 minus R. And in the last one, we got C 1 minus R was equal to 3 over 1 minus 1/4 or equal to 4, right? So does this sum, because it's the same pattern, it's still C over 1 minus R, it's still 3 over 1 minus 1/4, this is also equal to 4? And the answer is no. And this is why I'm trying to show you this. If you look at the formula very carefully, I'll zoom in so you can look at it carefully along with me. It says that if you start at 0 and go to infinity, the sum is exactly C over 1 minus R. So only if you start at 0 and go to infinity do we know the precise sum is C over 1 minus R. For our case, our example previously was, zoom, n equals 0 to n equals infinity of 3 over 4 to the n, which is 3 times 1/4 to the n. That sum is indeed 4 because it started at 0. This one does not start at 0, so its sum will not be 4. What will its sum be? Even though it doesn't start at 0, we can very quickly deduce what the sum is, because the only difference between this new series that's in green, if you're color sighted, the one down below, compared to the one above in blue, the only difference is it's missing the 3. This is a 0 here instead of a 3. It's missing the number. So whatever the sum is in blue has to be 3 more than the sum of the greens, right? The green's going forever too, right? So the sum of the green stuff and the sum of the blue stuff, they're all the same terms, except for the very first one. The top one has 3. The bottom one doesn't have the 3. So if the top one has a sum equal to 4, for this guy right up here, then what must the sum of this bottom guy be? Well, it's the same sum, but it's missing 3. It's got to be 4 minus 3 or what? So if your geometric series, if your geometric test starts with n equals 0 and goes to infinity, we know exactly the formula C over 1 minus R. If it does not start at 0, it starts at some other number, you can very quickly deduce what it is just by writing out some terms and saying, okay, well, they're the same thing, except this one's missing the 3, or this one's missing whatever number happens to be missing. And then you could do a quick calculation of what your other series adds up to be, even if it doesn't start at 0. They will be asking you something like this on the homework, so I did want to show you how to think about it on the lecture. Okay, so there's an example of finding the sum of a geometric series where it does not start at 0. All right, the rest of the video will not be as long, so we are getting, even though we have a few more examples to go, it will go much faster now because I'm going to be explaining a lot less and just doing a lot more in terms of calculations. So hopefully your patience will last a little bit longer to see 4 more examples. All right, so let's just get started. So we have 2 to the n over 3 to the n. This doesn't look like anything. We can do a limit. Always nice to do the divergence test. So we do 2 to the n over 3 to the n. This is infinity over infinity, which we could use L'Hopital's rule, but it's much easier to simplify this using algebra. So it's a good time to practice your algebra. 2 to the n over 3 to the n is also called 2/3 to the n. And if you have a fraction, like 2/3 raised to the n, 2/3 times 2/3, it gets smaller. 2/3 of 2/3 gets smaller. You take 2/3 of that, it gets smaller. So this limit tends to 0. So our divergence test tells us nothing. I call a divergence test fail because it failed to give us a conclusion. So divergence test didn't tell us anything, but it literally took us 15 seconds to do it. So it's good to try. So is this a geometric series? The answer is it is, yes. So we can write this series. Again, I'm managing space poorly. So we can write this series from n equals 1 to infinity as 2/3 to the n, right? Using the same algebra we did before. And this is c times r to the n, where there's no c number. In other words, c number is 1. And the r, the constant being raised to an exponent, is 2/3. So this is the sum of c times r to the n, where the c value is 1 and the r value is 2/3. So we know that r is between -1 and 1. 2/3 is between -1 and 1. So this converges. As simple as that. It converges by the geometric test. It follows the format of c times r to the n, and the r value is between -1 and 1. So therefore, we know it converges. We're done. Converges. Yay. All right, next one, 5 to the n over 5 to the n plus 1. 5 to the n is a number raised to an exponent. 5 is a constant base. N is a variable exponent. That is geometric. That's exponential. It's the same thing. But we have an exponential on the top and an exponential on the bottom, and they have different exponents. So we have to learn our algebra on how to simplify this. There are several ways of simplifying this algebraically. I will show you one of them, which comes in quite handy other places as well. It's basically one of your exponent rules that most people think as one directional, but I'm doing it in the opposite direction. If I said something like, 3 to the 4th times 3 to the 5th, we would get 3 to the 9th. You add the exponents. So same base, you can add the exponents when multiplying those powers together. I'm going to basically be undoing that. So I get 5 to the n times 5 to the 1. Right? So 5 to the n times 5 to the 1 is 5 to the n plus 1. I just did it backwards. The reason why I did this is because now you can see the 5 to the n and the 5 to the n divide out. And I'm left with just 5 to the 1 in the denominator. Okay, so what does that tell us? So our original series of 5 to the n over 5 to the n plus 1 algebraically simplifies. We didn't do any fancy calculus. We just did some basic exponents, simplification, to 1 over 5 to the 1. Right? 5 to the n and 5 to the n divide out. All right. So 1 over 5 to the 1, by the way, is the same thing as just 1 over 5, because 5 to the 1 is 5, right? So this is just 1 over 5. Does the series of 1/5 converge? Does it add to a number? It looks like it is because it's 1/5. But remember, we're adding 1/5 plus 1/5 plus 1/5 plus 1/5 plus 1/5 forever, right? If you add 1/5 forever, does it equal a finite value? A lot of you might be able to reason no. If you group together 5 1/5, that's 1. You group together the next 5 1/5, that's another 1. So you can argue just by grouping things together, you're adding 1 plus 1 plus 1, which is going to be infinity. Or you can use the divergence test. Remember the divergence test? Right? We take the limit as n goes to infinity of this, this sequence that's part of our series, right? 1/5 is the thing we're adding together. You take that limit and you see what you get. Well, 1/5 doesn't have any ends in it. It's a constant. So the limit of 1/5 is in fact 1/5. And 1/5, in case you're wondering, is not equal to 0. Why is that important? Because the divergence test says that if the limit of the sequence is not equal to 0, for example, 1/5, then we immediately know that the series has to diverge. So the series, the original series, as well as this 1/5 series, diverges. Diverges. I think I spelled that right. Okay. Next up, we have 2 times 3 to the n. 2 times 3 to the n is another c times r to the n, where the c is 2 and the r, that sort of, base number, is 3. So this is 2 times 3 to the n, c times r to the n, where c is equal to 2 and r is equal to 3. Notice that R is not between -1 and 1. So R is not between -1 and 1. It's specifically bigger than 1. And the geometric test says, if you want to go back and review the geometric test, the geometric test says that if R is bigger than 1 or R is less than -1, we immediately know that the series diverges. That's basically the divergence test also, by the way. But they oftentimes just group it together with the geometric test. But no matter which one you're thinking of, we definitely know that this thing diverges. So let me put a little line here so it becomes a little clearer where I'm doing. So in this particular situation, R is 3. R is not between -1 and 1. So we immediately know that this series, the one we're analyzing, 2 times 3 to the n, diverges. And that diverges by essentially the geometric test, or you could also argue it by the divergence test, either one. My last example for this video is this one over here. I will zoom in a little bit and I will make space below it. All right, 2 to the n plus 3 to the n plus 1 over 5 to the n is our series that we're adding together. So what do we do with this? Well, we can do all kinds of things, but I was trying to show some algebra as a key component to simplifying these series. So we have 2 to the n plus 3 to the n plus 1 over 5 to the n. This is a distributive property problem of division. So I can write this as 2 to the n over 5 to the n and 3 to the n plus 1 over 5 to the n. You can also think of this as unadding fractions. You have the same denominator, 5 to the n. You add the numerators together. I'm just doing the same thing backwards. I'm unadding these. They have the same denominator, and I separated the 2 to the n plus 3 to the n plus 1. It's really the distributive property. I'm dividing each of these guys by 5 to the n and writing them as separate components, separate terms. Okay, so let's look at this. This first thing, 2 over the n to 5 to the n, remember how to simplify that. That's 2/5 to the n. That's how you simplify 2 to the n over 5 to the n. The next one, I'll just write it as a separate sum. This n equals infinity. This is 3 to the n plus 1. If you remember, 3 to the n plus 1 is 3 to the n times 3 to the 1, right? That's one of our exponent rules. 5 to the n is still on the bottom. And now I can group the 3 and the 5 together. So this is the sum of 3 over 5 to the n times 3. And if you don't mind, I'll put the 3 in the front instead of in the back. I could do that because multiplication order doesn't matter. And so our second part of the series is just 3 times 3/5 to the n. The first guy here is 2/5 to the n. Okay, so check this out. This first series, 2/5 to the n, 2/5 to the n is a geometric series. This is 1 times a number raised to an exponent. This is geometric. It is a geometric with a p-value equal to 2/5, which is definitely between 1 and -1. So we know that it converges. What about the second one? The second one, this is a time symbol, by the way. Looks kind of messy, but it's 3 times. This is also geometric. This one here is 3 times 3/5 to the n. This is also geometric. The 3 is our constant value c. Our p, oh, not p. Why did I say p? It's our r, right? We're using r for the base value, right? R is 2/5. So in this case, r, if I can get my letters straight, is 3/5, and 3/5 is once indeed between -1 and 1. So each of these parts converge. Each of these equals a finite number. So the 1 times 2/5 to the n, that's a number. the 3 times 3/5 to the n, that's a number. What if you add two numbers together? You get a number, right? So you get a number plus a number is a number. So therefore, we know each of these converge. So this converges, this converges. Converges means it adds up to a finite number, a single number, right? Whatever that, we can figure out what the number is because we know the formula, but it doesn't matter. We're just trying to say whether it converges or not. I spelled converges wrong. Converges. So both of these things converges. So the original series, 2 to the n plus 3 to the n plus 1 over 5 to the n, converges by the geometric test. And I'll say times 2 because we used it twice, right? We did the geometric test twice to find out that each of those parts added up. So the whole thing adds up to a finite value, and therefore it converges. That word right there, which is very hard to read, even by myself who wrote it, is supposed to say converges. Converges. And that is today's video on section 11.2, where we're looking at some basic series, deciding whether they converge or diverge using various arguments, including the divergence test and the geometric test. So I'll try to zoom out a little bit so that you can get a small picture of everything, and then I'll zoom in to each of the top and bottom segments individually. I hope you found this video helpful, and I do hope you reach out if you do have any questions or want to do any extra practice or have any what-if scenarios where you're trying to see if you can better understand how to find the convergence and divergence of series. All right, well, there you go. And I hope you have a very enjoyable day. And I hope to see you sometime soon, either in my Zoom hours or on the next video.